Usually, harder questions could be made by combining two or three different ideas in physics, and this problem is going to illustrate that how we are going to combine to find the work done through the graph of force and displacement, and then using the work energy theorem to find the kinetic energy, right? So these are interconnected ideas from the same chapter. So let's look at the problem and try to solve it. So the question says a force F acts on a body of mass 2 kilogram, which is initially at rest. Okay. The graph shows how the force varies with the distance traveled along a straight line. So we are given a graph of force versus displacement. So clearly we know that if we are going to find the area, right, we are going to get the work done, right? That is in the previous problems we have looked at, right? So the area under the curve of the force displacement graph can simply give us the work done. So that's what we're asking, right? Find the work done by this force. So that's pretty easy. We can simply find this area and we get our answer. Part B says calculate the final speed of the body, right? So the work done also equals to the change in kinetic energy, right? And if you can, which means the final kinetic energy minus initial kinetic energy, right? So here we have to find the speed. So if we can find the final kinetic energy, we should be able to find the speed. For that, we will also need initial kinetic energy. So let's look back in the question and says if we have some information about the initial kinetic energy. So it says a force F acts on a body of mass 2 kg initially at rest, right? So which means my initial kinetic energy is 0. So that makes our life easier. So what we are going to do is that we are going to find the work done through the area and going to make it equal to the final kinetic energy because that is equal to 0. So that's going to be half mv square, and m is given, so we should be able to find v square, right? So that is what we are going to do, and that is what is going to be our strategy, right? So let's start by part A. For the part A, we have to do is find the work done, and then we can find the work done by finding this area, right? So this area has three parts. The first is this triangle, right? So that triangle is going to be half into the base, which is 5, into the height, which is 8. Okay, so that's 4 and that's 20 joules. Part B has this part, right? This is a rectangle. This is 5 and it's somewhere, I think, roughly around 12, right? So 12, 13, 14, 15. Okay. So with that, this part is going to be 12 minus 5. So that's 7. And the height is going to be 8. So this rectangle is going to be 7 into 8, right? So 56 joules. And this triangle, again, third one, which is the height, again 8, but how much is the base? So this is 12, this is 15, then this base is 3. It's going to be half into 3 into 8, right? So 4, that's 12 joules. Okay. So now we simply add it up. 12. Okay. So that's 88 joules of work. And that is going to be equal to my half mv square. So with that, we can find the velocity. So let's do that. So part 1 is done. That's 88. Part 2 is 88 joules is going to be half m into v square. And my m is going to be 2. So that's easy now. So half into 2 into v square. So this will cancel. So my v is going to be square root of 88. Okay. As simple as that. So the square root of 88, and that is 9.38 or 9.4 meter per second. Okay. So you can see the problem which looks difficult, if we just try to break down our thoughts and see how the different concepts are getting interconnected in a particle problem, we should be able to solve this pretty easily, right? So in this case, you have to know two things, that to find the work, all you need to do is to find the area under the curve of fx graph, and then the work is also equal to the change in kinetic energy, and that's the very easily you should be able to get to the solution.